This video is going to cover attack rate. So the attack rate is just the risk of disease in an exposed population, and a risk is just a probability. So just kind of going over that again, it's just the number of cases over the number of people that are susceptible. But the attack rate is just finding the risk in the exposed. So the only difference here is just that it's the number of exposed cases over the number of exposed and susceptible. And when we say susceptible, we mean like it's possible for them to have become cases. It might not be possible for some people because they're immune, or because maybe the disease only affects like a specific sex or age group. And this is really useful in outbreak investigation, and that's easiest described with an example. So let's say there's an outbreak of food poisoning following like a Thanksgiving dinner. We could find the attack rate for each of these foods, and that could give us a hint at which one was the source of the outbreak. So what these attack rates would mean is that like 60% of the people who ate pumpkin pie got sick, 60% of the people who ate turkey got sick, but 90% of those who ate mashed potatoes got sick. So that gives a good indication that mashed potatoes might have been the source of the outbreak. So this is what a table might look like for calculating attack rate. So each of these rows is a person who is at the dinner. That first column is their sickness status, so whether they got sick following the dinner. And then we have each of the things that they ate. And these could be coded with zeros or ones, but I'm just putting Y for yes or N for no. So finding the attack rate for pumpkin pie, we'd look at the number who are sick who ate pumpkin pie divided by all of those who ate pumpkin pie. So I usually find the denominator first, just because the numerator is a subset of those. So 8 people ate pumpkin pie. 1, 2, 3, 4, 5, 6, 7, 8. And of those, the number that were sick also having a Y next to them. 1, 2, 3, there were 5 of them. And the attack rate, 5 over 8, comes out to 0.625. You can go through a really similar process with turkey that I'll just kind of rush through. So just calculating the number, finding the number of people who ate turkey, 8. And the subset that got sick was 5 of those people, so it comes out to the same attack rate, 0.625. For potatoes, these first 8 people all ate potatoes, and of them, the first 7 got sick, so 7 over 8, 0.88. So that's how we would find attack rate for the different meals, or the different dishes that were served, and you can figure out which one represents the highest risk, I guess. So you'll notice that if potatoes were the problem, why were some of the other attack rates like above 50%? Like the main reason for this is just that a lot of dishes kind of like co-occur together. So the example I gave here is like if gravy was the issue, then all of the different things at the dinner that you put gravy on, like potatoes and turkey, are all going to have a pretty high attack rate, even though the only one that's the actual problem is the gravy. So that's something you'll need to kind of think through when you see that a few things have similar attack rates. You just need to think of the possibility that they might not all be a source. If the sample size is really low for a certain dish, it's the attack rate has less meaning. So like if only 2 people had the salad or something and one of them got sick, that's not really enough people to say that the salad like truly is getting 50% of people sick. That might just be a function of only having 2 people. Also, something I kind of touched on earlier is just that the denominator needs to only include susceptible people. So an example that involves having to take away some of the people who aren't susceptible, we have in a daycare 5 children who developed chickenpox played with Lego, and 15 children played with Lego in total, and 4 had chickenpox before. So just kind of pulling information out of that, we have our numerator, just the number sick and exposed, 5. The number played with Legos in total were 15, but of those, 4 were ineligible to become sick, presumably because they've had chickenpox before and are now immune. So now we can subtract those 4 from our population exposed, and we get a attack rate of 0.45. So, wait, yeah, and yeah, the secondary attack rate is the risk of infection, I guess, for a given contact, for those coming into contact with a primary case. So this is easier to explain with a diagram. So let's just say someone at the dinner we were describing becomes sick. They're not, basically, that's the extent to which they're involved in the secondary attack rate. For the secondary attack rate, they are the source of infection. So it's all these people that came in contact with this primary salmonella case, and um, basically we can figure out the secondary attack rate based on like the number of people who got sick. I guess let's just say each of these people had one equivalent contact, like one contact where they had like a similar risk of developing the disease. So the number of sick who came into contact over the number who came into contact, so uh, 2 over 5.